Welcome to the 2008 UAS Spring Forum on Sustainability. Brought to you by the International Polar Year and UAS. Our first speaker is going to be Scott Waterman. He's coming to you from Anchorage, I hope. We'll see how that works. I've never tried this before. I've worked with Scott for maybe 15 years or so. He's the state energy manager with Alaska Housing Finance Corporation. He runs the whole package there. You know, not only does he put together low-income weatherization loans for communities and individuals around the state, he oversees our home energy rating system. He oversees our energy standards within the building energy efficiency standard for the state of Alaska. He speaks all over the state on indoor air quality, thermal, mold issues. Scott also walks the talk. Not only is he a bureaucrat, he's also built a number of passive energy efficient buildings for over 25 years. So it's really a pleasure to have someone like Scott who's willing to take our causes forward and to battle all the different interests that we have out there that are trying to say, you know, this is right, but it costs more sometimes. And it's a tough choice sometimes, but we're moving down that path. So I hope you're there, Scott. I'm going to see if I can make this work.
This morning we're going to be talking about energy supplies and the cost effectiveness of energy efficiency. But before we go there, we're going to be actually focusing on a concept called peak oil. And Markham, if you want to take us to the next slide, I'll start off with introducing the concept of peak oil. Peak oil is when the global production falls, when the loss of output from countries in decline exceeds the gains in output from those that are expanding. That's from Chris Skabowski of the Petroleum Review in London. And what we're facing here, next slide, is we need to be clear on the scale of the problem in order to maximize the solution. Because, of course, fossil fuels are finite. And when we reach the peak of production, fossil fuels become much, much more expensive. And rather than being in a case of expanding supply as production continues to grow, as we've seen over the last 140 years or so of the oil age, we're now going to be going into a period of decline, where production is actually going to be declining after the peak. And as those supplies diminish, the price goes up and someone is going to have to go without. So we're going to start to see the potential for resource wars. And our economy has revolved around cheap oil since the beginning of the 20th century. And it has permeated virtually every level of our economic lifestyle. And so as the price of oil rises, things will change, and they may change quite dramatically. And then finally, climate change is driven in large part by fossil fuel burning. So next slide, we move to Alaska, and we start looking at the problems that are going on in Alaska. Contrary to the myth of the rugged independent Alaskan, we're very dependent on the supply chain to bring us food, groceries, and supplies from the lower 48 and other parts of the world. And we live at the end of that supply chain. Our energy costs are up and rising rapidly. Some of our villages are paying in excess of $8, $9, $10, even $11 a gallon for heating fuel. And some villages are paying up to 65 cents per kilowatt for electricity. I believe the rate in Juneau is about 12 cents a kilowatt. In Anchorage, it ranges between 11 and 13 cents. Fairbanks is around 12 cents as well. We have a lot of conversations going on in the legislature in Juneau right now about natural gas from the North Slope. We have climate changes, which are more prevalent here than in any other part of the planet, except perhaps Antarctica. Alaska is kind of the canary in the coal mine for climate change. We have villages like Kivalina, Newtok, Shishmaref, and Unalakleet eroding into the sea or actually being threatened by rising sea levels. We have issues around drilling in the Arctic National Wildlife Refuge and, of course, the North Slope natural gas pipeline. Where should it go? How should it be built? Who should pay for it? And all those issues. Next slide. So in the United States, we have less than 5% of the world's population. However, we use more than 25% of all the world's energy, and we produce more than 30% of the carbon dioxide or the greenhouse gases. As we compare that to countries like Japan, Germany, United Kingdom, we see that we're using almost twice as much energy per capita as people in those countries. Next slide. So most of that is oil. And in 1859, when Colonel Edwin Drake drilled the first oil well in Titusville, Pennsylvania, he actually did something that changed the world. It was something that he probably didn't realize it at the time, but prior to that, newspapers and headlines across the country were saying energy shortage looms. Oil prices $2.50 a gallon. This is in the 1850s, mind you. And oil prices at $2.50 a gallon in current dollars in the 1850s. That's a big hit. What they were talking about was whale oil. So when the first oil well came in, it came in at a veritable gusher of about 10 barrels a day. And it, about the same time that a Canadian chemist figured out how to crack crude oil and produce kerosene, and the kerosene age and the oil age was actually born. So oil since then has allowed for tremendous productivity. There's over 23,000 hours of human labor equivalent in a barrel of oil. It's one of the most dense energy resources that we have on the planet. And it became an engine, a driving force for economic growth. It created incredible military power, mobility, and generations of thousands and thousands of amazing products that the world had never seen before. And of course, anything like that on that scale, there's both good and bad in it. And when you think back to the era of the early wildcatters in, say, Spindletop in East Texas in the 1920s and 30s, they run a well in. There's actually a movie out. I just saw the trailer for it last night. Something about No Room for Blood or something like that. Anyway, it's about oil drilling in Texas in the 1930s. When you think about that, when those wells came in, they would be a veritable gusher. They would be rising 80, 100 feet in the air. Guys are shooting out of the ground. That it didn't take a lot of energy needed to extract it. So one of the things that we look at is the energy return on energy invested. And that's the amount of energy that we need to put in to produce oil or any other energy force. So when we think about the Spindletop in East Texas, 1 barrel of oil would produce approximately 100 barrels, or 1 barrel of energy equivalent would produce approximately 100 barrels in 1930. Today, that stands at about 10 to 1. It takes about 1 barrel of oil to produce 10 barrels of oil. So we're off about 90 barrels of oil since the 1930s. When we look at things like, well, what about the tar sands in Canada? It takes about 2 barrels of oil to produce 3 there. And there's a huge push for ethanol from corn, and that's maybe 1 to 1. It takes about 1 barrel of fossil fuels to produce 1 barrel of corn, or ethanol from corn. So the energy return on energy invested is an important concept. In 1973, the Arab oil embargo interrupted production and flow to the United States. Supplies were interrupted about 9%, and there was widespread panic. Gasoline prices skyrocketed up to about 50 cents a gallon. And we had another interruption in 1979, and the price of gasoline went over $1 a gallon. There was about a 4% disruption in supply at that time. At the time, President Carter declared that oil was vital to the national security interests of the United States, and by any means necessary, the U.S. would maintain access to the Persian Gulf oil fields. That became known as the Carter Doctrine, and it has been maintained by every president ever since. Oil is vital to the national security interests of the United States. In 1971, America was only importing about 8% of its oil from other countries. Today, we're importing over 65%, and that number is rising. Costs are up, volatility is eroding, and our balance of trade deficits is skyrocketing. It's nearly $800 billion today, with over $300 billion of that just for energy alone. And the U.S. Department of Energy has estimated that each $1 billion in trade deficit results in the loss of 27,000 jobs going overseas. So we're looking at nearly 7 million jobs going overseas because of our oil imports alone. And then, of course, our national security interests are threatened. You can move a couple slides ahead, Markham. Imported oil today is global demand is about 85.7 million barrels a day, and our supply is right there. And we got to remember that while individual countries can import oil, the world cannot import more oil. It's a finite resource, and production has remained fairly flat for the last several years, since about May of 2005. There has not been any increase in production, and think about what has happened to the price of a barrel of oil since May of 2005. It's more than doubled, from under $50 a barrel to over $100 a barrel. So in all that, in the past, whenever there's a dramatic rise in price like that, a doubling in the price of oil, we find the amount of oil that's being produced rises fairly quickly. But in the last 2.5 years, as we've seen tremendous rise in the price, more than doubling in the rise of the price of a barrel of oil, we've not seen any increase in production. Next slide. So what we're seeing now is not the end of oil, but the end of cheap oil. And as we hit the peak of production, next slide, we start to see the end of cheap oil. And this article in Scientific American came out in March of 1998. And what we're looking at here is kind of the Hubbert curve, and I'll explain that in a moment. The Hubbert curve looks at where we hit the maximum production that we're ever going to see. And the prediction is that we're going to hit that somewhere between 2010 and 2020. A lot of people are looking at, we may already be into it now. Next slide. This theory was promoted and initiated by Marion King Hubbert. He was a geologist for Royal Dutch Shell in the 1940s and 50s. And he began to look at the flow from oil fields. He realized that when a field was about halfway through its recoverable reserves, that no matter what technology you introduced to that field, production would maximize at a certain point. So after that, it would begin to decline when the field was more than halfway through its production. So we're seeing many fields around the world that are more than halfway through their production, and after production rises to a peak, it can never be surpassed. And then it continues to decline until the field is abandoned. Next slide. So in the 1940s and 1950s, he was pretty roundly criticized. In 1956, he made a presentation before the Petroleum Engineers of America, the Society for Petroleum Engineers, and he predicted that in 1956 that the United States would peak in its lower 48 production by 1970. Well, he was very roundly criticized until people realized that he was only off by about 8 months. The United States lower 48 production actually peaked in 1971. And one of the other things that he postulated is that the second half of oil is much more expensive to produce than the first half, and that's been shown to be true over and over again. So the big question in all of this then is, what are the recoverable reserves that we have today? And that is a huge question. The production growth in oil has nearly flattened out, as I said. Actual production's been flat since May of 2005, but demand is expected to increase to over 120 million barrels a day, according to the Energy Information Agency and the International Energy Agency, by 2020. So you can skip ahead a couple of slides to the next graph. And herein lies the problem. We have the red zone is our demand, and that demand is expected to rise up to about 120 million barrels a day. Our current oil production from known deposits, the yellow part of the graph, is expected to decline by 2020 to about a little more than half of what we're doing today, somewhere around 50 million barrels. Now, there is new technology that's going to bring in some additional oil when we start looking at various ways that we can drill, bottle brush drilling, and nitrogen and natural gas injection and seawater injection into wells. We can enhance the oil recovery and get more out of the reserves than was previously possible. And that's going to make up some of the difference. And then there's also some undiscovered oil out in the world, for sure. And then conversion from other sources, coal to liquids, natural gas to liquids. But it's not going to be enough to make up the increase in demand. And so we start to run into shortages. Next slide. Furthermore, we have some highly suspicious numbers of reserves around the world. In the middle 1980s, the price of oil in the late 70s had risen to up around $40 a barrel up through the early 1980s. And as I mentioned earlier, when in previous price rises, additional oil was produced, and all of a sudden there was a big collapse. We saw the price go from about $40 a barrel to about $9 a barrel in 1985. And for those of you that were around in Alaska at the time, it caused a tremendous recession. We had 11 bank failures here, and we had over 5,000 homes foreclosed upon. And we had tremendous problems here. Well, also all the oil producing countries, the Organization for Petroleum Exporting Countries, and all the other oil producing countries went through the same problem. Their revenues dropped substantially. So OPEC got together and decided that they were going to limit the amount of production based on the number of barrels of oil they had in the ground. So it was going to be a ratio. If you had more oil in the ground, you could produce more. Saudi Arabia, being the holder of the world's largest reserves, was allowed to produce the maximum amount of oil. And what happened was, shortly after that agreement was signed, Venezuela, Iraq, Kuwait all doubled their reserves reporting. Abu Dhabi tripled theirs, and Saudi Arabia's increased by about 50%. Well, it's just turned out recently that Kuwait adjusted its reserve numbers and came back to the realization that in the 1980s, when they had doubled their reported reserves, it was completely fictitious, and their actual reserves were about half of what had been reported for many years. So the reserve information is fairly inaccurate. There's a lot of politics, economics, and secrecy. But when we look at the next slide, and we see that conventional oil discovery in the United States, conventional oil discovery peaked in the 1930s. In the world, it peaked in 1964. And we've been seeing a steady decline of new discoveries of oil ever since. Next slide. And furthermore, we've seen a dramatic decline in the number of large oil fields, the giant and supergiant oil fields like the North Sea and Prudhoe Bay. The discoveries of new fields like that have been declining precipitously. And next slide. We find that oil discoveries have lagged significantly behind consumption every year for more than 20 years. And discoveries are only replacing about 33% of new production. So, for example, last year, the world used over 31 billion barrels of oil, but only found about 10 billion barrels of new production. So how long can we sustain that? This whole session this morning is about sustainability. That is not sustainable. If you continue to spend more than if you write checks on your checking account without making deposits, or making fewer deposits than you're writing checks for, it's not sustainable. Pretty soon you're bouncing checks. Well, pretty soon we're going to start bouncing oil production. Next slide. So continuing on with oil discoveries, there was no major oil field finds in 2004-2005. In 2006, there was a fairly major field discovered in the Gulf of Mexico called the Jack Field, but production costs alone could run over $50 a barrel. And in Saudi Arabia, the production costs are about $3 a barrel. So that's significant. Furthermore, that Jack Field is 7,000 feet underwater and 20,000 feet deep into the ground. It may be as big as Alaska's Prudhoe Bay, but it's very expensive to produce. Another field was discovered in 2007 at about 8 billion barrels estimated, and that's the Tupi Field in Brazil. It's also 7,000 feet underwater and 16,000 feet deep. So what we're finding is, yes, we're going to find more oil out there, but it's in smaller quantities, it's in deeper wells, and it's in deeper water offshore, and there's more gas and less oil. That's significant. So our discoveries are declining and our demand is increasing. Our production is also holding flat right now. This has significant effects, next slide, on things like air travel. Jet fuel costs in 2002 were 50 cents a gallon. In 2004, they were over $2 a gallon. No business model of any airline can absorb $90 to $100 barrel of oil, according to James May of the Air Transport Association. Oil closed yesterday at $102. So that means that air-accessible tourist destinations like Juneau and Anchorage and Fairbanks are going to start to decline as the price of airline tickets continues to rise. On the farm, next slide, modern agriculture is the use of land to convert petroleum into food, according to Albert Bartlett. Wheat prices have hit over $12.50 per bushel, where they were $2.50 per bushel about 5 years ago. It currently takes over 10 calories of fossil fuel to produce each calorie of food in the United States. So we've added a tremendous amount of oil to our food. Next slide. All of our commercial fertilizers and pesticides are made from oil and natural gas. And natural gas has also peaked in North America, which is why there's such a push to build offshore liquid natural gas import facilities. And the federal government has taken over and kind of told states that state rights don't matter. If the federal government decides that we need an offshore liquid natural gas import facility off the coast of your state, you're going to get one. Farming implements such as tractors and trailers are all constructed and powered using oil. Food distribution networks are entirely dependent on oil, and especially in Alaska. The average piece of food travels 1,500 miles in America from the farm to the plate, and in Canada and Alaska that number is 5,000 miles. Alaska, including subsistence foods, produces just 3% of its own food. So we could dramatically increase our own food production here as a sustainable measure, and I would really like to emphasize that point, that as the price of oil rises, we are going to have to begin to dramatically improve the amount of food that we grow in Alaska, increase the amount of food that we grow here. In the former Soviet Union during a collapse, I had a long conversation with a woman who had gone through that the other night. And she said that what kept people going during the collapse of the Soviet Union was that every flower pot, rooftop garden, apartment deck garden that could be utilized was utilized for growing food. and they grew potato, cabbage, carrots, and beets, and they were able to survive. Those root crops are ones that can sustain people for long periods of time, and they can keep throughout a winter. And food production is an incredibly important piece of sustainability. Next slide. Climate change. Munich Re, one of the largest reinsurers in the world, has paid out more than double its insured losses in 2007. But 2005, they had $99 billion in economic losses from hurricanes Katrina and Rita. And economic losses topped over $220 billion. This is in many forms because of climate change, and the insurance companies are recognizing it. So the doom and gloom part of the presentation is over. What can we do? Next slide. Wind energy is one of the fastest growing sectors of the energy industry. It's cost competitive now with fossil fuels. The system size is growing dramatically. The problem with wind, of course, is that it doesn't blow all the time. It doesn't blow consistently at a consistent rate. So we have a problem with when the wind is not blowing hard enough, we are not producing as much electricity. Next slide shows a graph of Alaska, and it doesn't show southeast Alaska, but this shows the wind regime. The blue, the red, the purple on the graph all show good wind regimes where wind is economical. So in Alaska, we're starting to see a lot of new wind turbine projects that are going into Alaskan villages. In Anchorage, there's talk of a wind project on Fire Island, which would perhaps reach 100 megawatts installed capacity. There's another one in Healy Creek, Eva Creek near Healy, up on the Parks Highway, that could have as much as 100 megawatts. So that's one possibility. In Alaska, solar energy, next slide, is something that is probably usable about 9 months out of the year. You're going to get a little bit less in the cloudy areas of the maritime provinces or the maritime areas of the state in the southeast and along the coast, but there's a lot of solar energy falling in Alaska. It's currently used, next slide, for a lot of railroad crossings, park buildings, and remote cabins. But as the price of oil increases and the price of silicon and solar power comes down, we're going to start to see some changes in that. And there's also some increased promise with some new silicon nanowire batteries that may increase the storage capacity of batteries by about a factor of 10 over the current lithium-ion batteries, which are quite a bit more powerful than the current nickel-cadmium batteries. So there's a lot of promise in solar on the near future, but it's not coming quite yet. Next slide, and skip ahead to the following slide as well. Geothermal in Alaska. There's a project being discussed near Dutch Harbor where the McCushkin volcano would be tapped, and it could provide the entire heat for the entire community and electricity, and possibly have hydrogen as a potential export. A similar project is being looked at here in south central Alaska, tapping Mount Spur and Lake Chakachamna as a combination hydroelectric and geothermal electric generation. There is enough heat that could come off of that project to heat the entire city of Anchorage, melt all the road ice, and heat enough greenhouses to feed the entire city. That was an exciting project. I would love to see something like that. The president of Iceland was here in October and left a proposal with the governor and Department of Natural Resources Commissioner Tom Irwin. I hope that something like that is moving forward, at least being looked at. Next slide. Hydropower in Alaska is definitely a good possibility. There's currently dams in Kodiak, Wrangell, Glen Allen, Ketchikan, Bradley Lake, Eklutna Lake, and Cooper Lake in south central Alaska. There's a proposal to look at Lake Choctawhamna, potentially a 330 megawatt power plant in south central Alaska. The permit process is already underway by TDX Corporation. And the Susitna Dam is back on the table once again. Boy, the more we change, the more things stay the same. When I first got into the energy business in the early 1980s, energy costs were really high. We were talking about all kinds of energy efficiency, and Susitna Dam was the talk of the town. It's back on the table again. Next slide. We have huge resources of coal in Alaska and a few power plants running in Fairbanks, at Eielson and Healy, and also University of Alaska Fairbanks. Coal is high pollutant and causes a lot of carbon dioxide releases and mercury releases in the air. Carbon dioxide, of course, being a greenhouse gas, but the mercury is estimated by Harvard University to kill 30,000 people annually from the coal plants producing electricity in the United States. High acid rain is also causing a lot of problems in the northeastern United States. There is clean coal technology, but the Department of Energy just pulled all the funding for that. It's not there yet. And there is a clean coal plant in Alaska in Healy, but it sits idle at double its estimated cost. It was originally budgeted at $93 million. Currently, they have over $225 million invested, and the plant sits idle, not producing power. Next slide. There's a proposal for nuclear power in Alaska, in Galena. I don't know how actively it's being pursued, but the Toshiba Corporation has a 20 megawatt mini nuclear power reactor that they think they can scale down to 10 megawatts, and they're willing to test it out in a remote Alaskan community. And they're looking at gifting it to the city of Galena. It's a small plant. It can be barged in, lifted in place, and at the end of its 30-year cycle, the entire plant can be removed, and Toshiba has said that they will take care of the waste products. Next slide. Ocean Power. Leases are currently being let in Lower Cook Inlet to do feasibility studies on tidal power. New systems are going in. New system was just christened off the coast of Ireland this last couple of weeks, and I saw a story about it yesterday. So ocean power is coming into play. The nice thing about ocean power is sometimes if you have both good tidal regime and a good wind regime, you can put both wind turbines and tidal turbines on the same facility. Next slide. Transportation. What makes more sense, Hummer or Prius? Neither. Let's keep going. Transportation uses, next slide, uses more than 28% of all the energy in the United States and over 67% of the petroleum. Cars and light trucks use the lion's share of that. Heavy trucks 16% and mass transit 24%. But the lion's share is used by our cars and light trucks. Next slide. Let me take you through a little assumption. If we were to tap into the Arctic National Wildlife Reserve, former Governor Murkowski and the U.S. Geological Service says that there's a 5% chance that there's 16 billion barrels of oil there. The Energy Information Agency says there's a 95% chance there's just under 6 billion barrels of oil. Let's split the difference and say it's 11 billion barrels. That's our assumption for this little exercise. Development and extraction would take 51 years to recover that 11 billion barrels. Next slide. But when we look at this graph, we see that if we were to close the improve the corporate average fuel economy and make the average fuel economy of vehicles sold in the United States 40 miles per gallon for 10 years, we could save 25 billion barrels of oil in that 10-year period. Furthermore, if we close the light truck loophole, we would save an additional nearly 10 billion barrels a year. Compare that to the 11 billion barrels that we might get out of the Arctic National Wildlife Refuge over 50 years, and you can see that we have more than 10 times as much oil potential from energy efficiency in our transportation than we have by drilling new areas of the Arctic National Wildlife Refuge. Furthermore, we can look at the oil that's coming out of a place like that and say, if we really need it, it might be worth a lot more 20 or 30 years down the road than it is today. So next slide. In our automobiles, 80% of the energy used in an automobile is lost in the form of heat and exhaust. Only 20% is used to deliver energy to the drive wheels, and of that 20%, only 5% is needed to move the weight of the driver. When we do the math, we find out that 1% of the energy is needed to move the driver. So if you spend $60 to fill your vehicle, $59.40 is used to move the vehicle around, and 60 cents is used to move the driver around. Cars burn their weight in gasoline each year. Next slide. Hybrid electric vehicles were first developed in the 1920s. And what we're looking at here is a picture of a 1921 Owens hybrid electric 60 touring sedan. They've been around for a while. They work. The current Toyota Prius and Honda Civic can achieve in excess of 50 miles per gallon. But the hybrid technology can hugely improve with that. And the next generation of hybrids is being looked at to achieve over 100 miles per gallon. Next slide. But that pales in comparison to what we could do. In the upper right-hand corner, you see the Opel Echo Speedster. It's capable of traveling at 155 miles per gallon and getting 94 miles per gallon. 155 miles per hour and getting 94 miles per gallon. The top left picture is a Volkswagen L1. Can travel 100 kilometers on 1 liter of gasoline. That equates to about 235 miles per gallon. Plug-in hydraulic electric diesel hybrids can get over 235 miles per gallon, but even that pales in comparison to the 2006 super mileage competition winner at 3,415 miles per gallon. We have the ability to go far beyond where we go today. Next slide. So the next thing I want to look at is looking at things like light bulbs. A lot of people will say that changing a light bulb isn't going to do enough. Well, they're right. We have to go a lot farther with changing light bulbs, but that still leaves no excuse for not changing the light bulbs. And this is a quick look at changing out 10 incandescent 75-watt light bulbs for 10 compact fluorescent 15-watt light bulbs. Same light output, but for 1/4 the energy use. The bulbs cost a little more. The compact fluorescents cost about 3 times as much, but they last 10 times longer. So in actuality, the bottom line, when you get down to the bottom, actual savings at 10 cents a kilowatt over 5 years for replacing 10 bulbs is over $1,200 a year. I mean, $1,200 for 5 years. Next slide. We can look at the same thing with refrigerators. And if we have an old refrigerator that uses 2,500 kilowatts a year, over a 5-year period, if you paid $50 for that old refrigerator, you'd spend over $1,300 to run that refrigerator over 5 years. By contrast, if you were to go out and buy on your credit card at 21% interest, a new energy efficient refrigerator that uses only 450 kilowatts a year, even paying the interest, you'd spend about $975, a savings of $325 over 5 years. Next slide. Our housing has improved dramatically. What this chart shows is the increase in the energy rating score from houses built in the 1950s and 60s to today. And the chart on the right shows that the cost of energy per square foot has dropped by half since in the houses built today versus those built prior to 1960. So we've made significant improvements in how we build our houses, but we can do better. Next slide. So what do we want? We really want an economy that has tremendous mobility. We want solid economy with jobs and prosperity. We want abundant, healthy food, locally produced, clean water, clean air. reliable energy systems that are sustainable for future generations, and of course, stability, security, law, and order. Next slide. If the United States were as energy efficient as Japan or Sweden, we'd be spending $800 billion less per year on energy at $80 a barrel. Weatherization creates tremendous economic development potential, far more than traditional tax incentives or infrastructure development that's considered economic development. That was from a study at Ball State University. Next slide. Energy efficiency is the foundation of renewable energy. The cheapest energy is that which we don't have to produce. Energy efficiency costs about $12 a barrel to save today, and the oil price today is over $102. If you want to find out more about this, look at www.oilendgame.org. It's a book written by Amory Lovins, and it's how to get the United States off of oil by the year 2030. It's $40 if you purchase the book, but you can download it for free from that website. Next slide. When we look at renewable energy that's produced locally, it creates good jobs with good wages and quality health care, and those jobs are not going to be shipped out. They're going to stay in Alaska, in your local community. We're reducing our reliance on expensive fossil fuels that are limited and probably declining. We're going to reduce our dependence on unstable countries producing oil and gas. We'll have cleaner water, cleaner air, reduced species loss, important for all Alaskans. We'll have new technologies and industries that we can begin to look at, and we may be able to start mitigating some of the climate change. Next slide. How do we get there? There's no silver bullets for this. It's a combination of efficiency, wind, solar, tidal, hydro, geothermal, and all the other renewables. Coal and nuclear are probably going to be promoted, but they have bigger drawbacks, and we need to look very carefully at those. Coal plants permitting in the Midwest has been delayed and dropped because of the climate change issues in the last couple of years. Tremendous change in the electric industry happening there. We need to really work on developing non-petroleum liquid fuels. I'm not sure biofuels are the way to go because the energy return on energy invested is just not there yet. I think we're going to really need to learn to power down and learn to live using less energies, which means we have to get much more efficient or use different forms of energy. How do we get there? Next slide. We increase our mass transit. We build denser neighborhoods, tighter community. We begin to interact like we need to. We're a relationship-based society, and our automobile cuts us off from relationships with each other. Mixed-use neighborhoods that have business and residential in the same area encourage walking, cut down on driving trips, and decrease congestion and crime. Next slide. So how do we get there? I'm not sure we can wait for the government. We each have to take our own part of it. Thinking globally, acting locally, buying locally is really important. Growing our own food or knowing someone who does that we can trade with. And by reducing our own energy use, we're in effect generating power. We're producing negawatts by not using energy. Negawatts is a term coined by Amory Lovins at the Rocky Mountain Institute. We can lower our own energy footprint, maximizing our efficiency and conservation. We can look at generating our own power or encouraging our local utilities to generate power from renewable resources. And I'd like to propose a vision for Alaska using our oil and gas royalties, which have really looked at those oil and gas royalties that have put over $40 billion into our permanent fund to create a renewable energy fund for Alaska. And something like that might look at improved hydroelectric, 330 megawatt Chakachama hydro plant, a 250 megawatt geothermal plant, 200 megawatts of wind at Fire Island and Healy. That can give us reliable, clean, fixed cost power for 40 years and also provide all the heat for Anchorage. And that would draw in companies like Google and Microsoft who have tremendous power requirements, and they need a lot of reliable power, and they need to know what they're going to be paying for power far out into the future. Renewable energy is an investment in Alaska that could bring good jobs and an interesting new technology industrial base. We could produce our own food in Alaska in greenhouses using geothermal heat to do that, and then turn around and export that technology. I think if we were to use some of this budget surplus that we have right now along those lines, we'd be far better off. And I think there is a better way to do it. We just need to find it. And with that, I'll open to any questions.
Scott, thank you for that presentation. Lots of facts and figures there, but I guess one that really stood out in my mind was a graph showing that the United States uses twice as much oil per capita than the United Kingdom or Germany. I mean, that wouldn't surprise me if you were talking about a less developed nation than Germany. So I can think of a number of reasons why we might use twice as much, but what do you identify as the major reasons that boost that percentage up so high compared to UK or Germany?
A number of different things that go on. One is that Germany has dealt with high fuel prices since the end of World War II. Their economy was quite devastated, of course, after World War II. They had the opportunity to rebuild, where the United States has a lot of buildings that are, a couple hundred years old and far less energy efficient. We're also far, far more reliant on automobiles than the European countries are. And our suburban sprawl is far greater than those in European countries. We also have not ever really taken energy efficiency seriously. And we have a lot of different ways that we waste energy in our buildings, in our automobiles, our prolific use of electricity for all kinds of our home electronics. I think the studies that I've seen, show that we watch TV far more than a lot of European countries do. So our entire lifestyle, I think, needs to be rethought a little bit. I was able to cut my own energy footprint by about 75% when I really began to look at it. I was commuting about 60 miles each way to work. I lived by myself in an energy efficient house, but it was a large house. It was 2,300 square feet, and I was living there by myself. I moved into Anchorage. I'm now within about a mile from my office, and I can walk back and forth to work. My fuel cost for transportation is cut by almost $1,000 a month. And I'm sharing a house with 2 other people. I'm planning on doing a major energy retrofit to that house this summer. And I have already, without that energy retrofit, cut about 75% off my fuel use by changing my lifestyle a little bit. And it wasn't giving up anything. I still own a car. I still live in a house. I have all the traditional appliances that most people have, except a television. And so I think there's a lot that we can do to make ourselves more energy efficient. Germany also has a huge program with tax credits to put renewable energy systems on individual buildings. And I would love to see something like that in the United States.
Come in over using distance technology from San Francisco from Rick Woke. He has a question about price signals. And at a clean tech conference yesterday in San Francisco, we talked about subsidy policy issues regarding prices of renewable energy. So his question is, including defense spending, what do you estimate is the unsubsidized price of oil now for Americans, Scott?
We spend over $137 billion a year within the defense budget protecting oil infrastructure. So we could rename our Department of Defense the Department of Oil Infrastructure Protection. We also have an incredible amount of lost local revenues because of the inefficiency in which we use oil, money that leaves our community, lost economic development. the last figure I've seen would add $8.35 a gallon to gasoline on top of the $3.50 we're already paying. So we'd be paying in excess of $12 a gallon if it was the real cost of oil was counted in the United States.
Waterman from the AKA, or the Alaska Housing Finance Corporation, and if you'll join me in thanking him, I think he can hear us if we clap if I hold the microphone out.